So welcome to the video lecture 7 where we will concentrate on some numerical problems on the various concepts of operators. So let us begin with the first problem. You are given two operators, A is equal to 4x square, a multiplication operator, and B is equal to d by dx, and the function f of x is equal to ax cube. Calculate a into b of f of x and b into a of f of x. Okay, so the solution, first we have to calculate a into b of f of x. Okay, as I already told you, the sequence of operation is very important. First you have to apply the operator which is to the rightmost corner, and then we have to move from right to left. So the definition is a of b of f of x, that is, what is a? 4x square into b d by dx of f of x, that is ax cube, that is 4x square. Let us apply the first operator first. Differentiate. A is a constant, so a differentiation of x cube is 3x square. Okay, so this written number or the term that I have written inside the bracket is the result of the application of the first operator, a into 3x square. Now this resulting function is applied by the second operator, a, which is a multiplication operator. So we have to simply multiply this term by the operator 4x square. So this comes as 4 into 3, 12a x to the power 4. Similarly, let us find out b into a of f of x. So the definition is b of a of f of x. Now we have to apply operator a first. So that is d by dx of a. Operator a is a multiplication operator 4x square into f of x is a x cube. So this is d by dx of, first let us apply this operator. It is a multiplication, so let us multiply. It becomes 4a x to the power 5. 4a x to the power 5. Now on this resulting function, let us apply the second operator b, that is d by dx. 4 is a constant, a is a constant, into differentiation of x to the power 5 is 5 into x to the power 4, so which is 20a x to the power 4. Okay, so we have evaluated a into b of f of x and b into a of f of x. Clearly you can see that the final results are not one and the same. So a into b is not equal to b into a. In the second problem, you are given with one operator a d by dx and one operand f of x is equal to sin x. We have to calculate the square of the operator a, that is a square of f of x. So let us use the definition. What do you mean by a square of f of x? What is the definition of square of an operator? You are applying the same operator two times. So a square of f of x means a of f of x, that is, what is a? D by dx of a, that is d by dx of f of x, that is sin x. So this is d by dx. Let us apply operator a for the first time on sin x. So d by dx of sin x is cos x. And on this resulting function, we have to apply the operator a second time, that is d by dx of cos x is minus sin x. So this is the value of a square of f of x. Okay. In the third problem, you are given two operators d by dx and 3x square, and f of x is equal to sin x. We have to verify whether the two operators commute with each other or not. How to verify? You have to find out a into b of f of x and b into a of f of x and see whether a into b is equal to b into a. Let us do that. Okay. First let us calculate a into b of f of x, that is, a is d by dx of b 3x square into f of x is sin x. Okay, so this is operator b 3x square, this is operator a. Okay, since you have product of two functions, we have to apply the product rule. So this will be first function into differentiation of second function, that is cos x, plus second function sin x into differentiation of the first function. Differentiation of 3x square is 6x. So therefore a into b of f of x is 3x square cos x plus 6x into sin x. Okay, now let us calculate b into a of f of x. That is, b is 3x square, a multiplication operator, of or into a of f of x, that is d by dx of f of x, that is sin x. So you have to apply operator a first, that is d by dx. So d by dx of sin x is cos x, and on cos x we are applying the operator b, which is a multiplication of operator 3x square. So this is simply 3x square into cos x. So if you compare these two results, you can clearly see that a into b is not equal to b into a. Therefore, the two operators a and b do not commute with each other. Two operators a and b do not commute with each other because a into b is not equal to b into a. Now in the fourth problem, we have to verify whether the given operator and the given function satisfies this condition called as eigenfunction. Okay, so whether the given function is an eigenfunction of the given operator, and if it is an eigenfunction, what is its eigenvalue. You are given two set of operators a and b and two set of functions f of x and g of x. Now we have to apply each of this operator on these functions and verify whether it is an eigenfunction or not. If yes, what is the eigenvalue? So as per the definition of eigenfunction, when a function operator a is applied on the eigenfunction, it gives back the same function multiplied by a constant. Okay, that such functions are eigenfunctions, and that constant obtained is called an eigenvalue. So let us verify by taking one by one. Okay, so let us first find out a of f of x, that is d by dx of sine 4x, which is equal to 4 into cos 4x. So this is not an eigenfunction because you are not getting back the same function. Now let us find out a of g of x, that is d by dx of e to the power 4x, which is 4 into e to the power 4x. Therefore e to the power 4x is an eigenfunction because on application of this operator it gives back the same function but multiplied by a constant. So the eigenvalue is 4. Eigenvalue is equal to 4. Now let us try b of f of x. b of f of x is d square by dx square of sine 4x, which is actually, this double differentiation can be written as d by dx of sine 4x. It is just like square of d by dx operator. Square of an operator means applying the same operator two times. So d square by dx square is nothing but applying d by dx two times, which is d by dx of sine 4x. Differentiation is 4 into cos 4x, which is equal to, if I differentiate it again, 4 is a constant, differentiation of cos is minus sine 4x. So here I have 4, already I have 4 here, so it becomes minus 4 into 4, that is 16 sine 4x. So we are getting the same function again. So sine 4x is an eigenfunction, but it is multiplied by a constant minus 16, therefore the eigenvalue is minus 16. Okay, similarly you can calculate b of g of x and find out that this g of x is also an eigenfunction of this operator b with eigenvalue is equal to 16. Okay, I leave it to you to cross verify yourself. Now this is a very interesting problem. You have a function psi, which is an eigenfunction of a linear operator a. Okay, you are having a linear operator a of which the psi is an eigenfunction and its eigenvalue is lambda. Okay, this is the given condition. Now you are supposed to prove that c into psi, the function c into psi, where c is a constant, is also the eigenfunction of the same operator with the same eigenvalue lambda. Okay, So what you are given, the given condition is okay, what you are given, that psi is an eigenfunction of the linear operator A with eigenvalue lambda. What do you mean by eigenfunction? When you apply a function by an operator A, it gives back the same function multiplied by the constant, and that constant is called eigenvalue. So here A of psi is equal to, so operator A applied on the eigenfunction, you get the same function back multiplied by a constant which is called eigenvalue, and they have given what is the eigenvalue, it is lambda. So A of psi is equal to lambda into psi. This is the given information, that is psi is an eigenfunction of operator A with eigenvalue lambda. What you are supposed to prove? You are supposed to prove that function c into psi, where c is a constant, this function c into psi is also the eigenfunction of operator A with same eigenvalue lambda. That is, you are supposed to prove that A of c into psi is giving back the same function c into psi multiplied by a constant, and that constant is same here, that is lambda. So you have to prove this equation, and you are given this information. Okay, so to prove that this is true, let us start with the LHS. The LHS of this is A of c into psi. Okay, what is A of c into psi? Okay, it is informed here that c is a constant. Okay, and it is also informed that A is a linear operator. So what is the definition of linear operator? Operator A is applied on a constant into a function. This will be equal to constant into operator A applied on the function. So this is the definition of linear operator. This is the definition of linear operator. Definition of linear operator, and this will be true only if c is a constant. So let us work out on this. This is c into what is A of psi. Since psi is an eigenfunction of operator A, according to equation 1, A of psi is lambda into psi. This is obtained from equation 1. A of psi is equal to lambda into psi. Now c is a number, eigenvalue is also a number, so you can interchange that number because multiplication of number is commutative. C into lambda or lambda into c, both are one and the same. So I will write it as lambda into c into psi, because I have just interchanged c and lambda. What is this? This is nothing but the RHS. Okay, lambda into c into psi is nothing but the RHS, which has to be proven. So what is the meaning of this? What is the implication of this mathematical equation? That c into psi is also an eigenfunction of operator with same eigenvalue lambda. Hence we have proved this condition. So in the sixth problem is to find out the commutator operator of the given two operators. So you are given two operators, one is a multiplication operator x and a differential operator d by dx, and you are supposed to find out the commutator operator of these two. What is the definition of commutator operator? It is AB is equal to A into B minus B into A. But in order to find out the commutator operator, we cannot use this equation as such, definition as such. So what we have to do is we have to select some arbitrary or random function f of x. So this equation is rewritten here. So commutator operator AB of f of x is A into B of f of x minus B into A of f of x. So by using this definition, we can find out what is the commutator of x and dx. So therefore commutator operator of x comma dx of f of x should be equal to A into B of f of x. So x into d by dx of f of x minus B into A of f of x, that is B is d by dx of A of f of x, that is x into f of x. Okay, so this can be written as x into df by dx of f of x minus, here you have two functions, so we have to use the multiplication rule. First function into differentiation of second function, okay, plus, but here you have minus, so it becomes minus second function into differentiation of first function, that is differentiation of x with respect to x, that is 1. So x into df by dx, x into df by dx gets cancelled, so you get minus 1 into f of x. Okay, you have minus 1 into f of x. In the LHS you have x comma d by dx of f of x, right? So if I remove this arbitrary function, because these functions were never given, we simply assigned some random function. If we remove this arbitrary function from this equation, we get the corresponding operators. X d by dx is minus 1 cap. So the commutator operator of x and d by dx is a simple multiplication operator. What is this multiplication operator? Just multiplying by minus 1. This is the commutator operator for x and d by dx. Now let us evaluate the commutator operator for these two operators, d by dx and d square by dx square. So again we are using the condition, okay, the commutator operator is a of b of f of x minus b of a of f of x, that is equal to a d by dx of d square by dx square of f of x minus d square by dx square of d by dx of f of x, which is nothing but, okay, first derivative on the second derivative, it gives third derivative of f of x with respect to x minus, okay, second derivative of the first derivative of the function. So again it is the third derivative of f of x with respect to x, which is equal to 0, but we write it as 0 into f of x, okay. So the commutator operator d by dx and d square by dx square of f of x is actually equal to 0 into f of x. It is actually 0, but we write it as 0 into f of x because, as we showed it in the previous problem, at the end we have to remove that function f of x from the final equation, so that we get the corresponding operator equation. So that is why, even though the final result was 0, I wrote it as 0 into f of x. So if I remove this function f of x on both the sides, you get the corresponding operators. So the commutator operator of d by dx and d square by dx square is, if I remove this f of x, you get the corresponding operator, which is a 0 operators. So the commutator of d by dx and d square by dx square is a 0 operator, and as I defined in the commutator operator section, that if the commutator operator is equal to 0, it means the two operators commute with each other. So d by dx and d square by dx square commute with each other. Now in problem number 8, we have to prove this equality, that is the commutator of two operators a square and b. What is a square? It is actually the square of operator a. So the commutator for a square and b is equal to operator a into commutator of a and b plus commutator of a and b into operator a. So to prove this condition, let us begin from the RHS of this equation and try to end up with this LHS. Okay, so the proof for this has to begin with the RHS. So let us consider a into commutator of a and b plus commutator of a and b into a. Okay, so as I already told you, it is very difficult to deal with operators alone. Okay, sometimes while dealing with operators alone, we make some most of the time we may end up making some mistakes. So it is always to add some insert some arbitrary function, and at the end you again remove that arbitrary function, and you will get the corresponding equation in terms of operators. So here also we will do the same thing. Okay, we can apply the arbitrary function, and at the end you can remove that arbitrary function. So you can do it any other way, but if you are confident that you can work out without the arbitrary function, you can do it. Okay, so let us try to simplify this. Okay, so this is operator A of, let us use the definition of commutator. Commutator of A and B is A into B minus B into A. Okay, this is the commutator of this particular operator, plus again commutator of A and B, it is actually A into B minus B into A into operator A. Now let us further simplify. Now let us apply operator A on the first term and the second term. So this is operator A of A into B, which can be written as A square operator B. Second term is operator A into operator B into operator A. Remember, you cannot interchange the sequence of these operators because we don't know whether the operators commute with each other or not. So you cannot interchange the sequence. So it is, first term is A into A square B. Second term is A into B into A, plus, now let us apply this term on this. So A into B into A. So again we cannot interchange the sequence. The last term is minus, the first is B into A, that is B A square. Okay, so second term minus A into B into A, and here plus A into B into A. Okay, they cancel out, so you get operator A square into B minus B into A square. If you look at this is actually a commutator of two operators. Okay, it is nothing but the commutator of A square and B operator. Okay, because commutator of A square into B is nothing but A square into B minus B into A square. First operator into second operator minus second operator into first operator. So this term is nothing but the commutator of A square comma B, which is nothing but the LHS of this equation. So we have proved this condition. The ninth problem is, we are given two operators d by dx into x square. So we have to find out, okay, simplify this expression and find out what is an expression for operator. As I already told you, while working with operators alone, we may lead to some mistakes while solving the operator equation. So it is always advisable to use some random or arbitrary functions to begin with the operator equation, and at the end, that is the final step, remove that function f of x again, so that we end up with the correct operator equation. So let us try to find out what is the expression d by dx into x whole square. So let us select some arbitrary function. Say for example f of x is a arbitrary or random function. So what is d by dx of x whole square when applied on this arbitrary function? Because operators are always applied on a function. So d by dx into x square of f of x, it is square of an operator. So what do you mean by square of an operator? You are applying the operator two times. So this is d by dx into x of d by dx into x of f of x. Okay, so this is square of an operator. What do you mean by square of an operator? You are applying the same operator two times. So d by dx of x into d by dx of x of f of x. So let us apply this operator on the function for the first time. So this is nothing but d by dx of x into x. This becomes d by dx. Here again you have multiplication of two operators. So the sequence is very important. The one that is to the right is applied first, and then that to the left is applied later. So this becomes d by dx of x into f of x. This operator, multiplication operator, is applied first, to you this function x into f of x, on which you have to apply the second operator. So this becomes d by dx into x into, let us apply the second operator on this, so it becomes differentiation of first function into differentiation of second function plus second function into differentiation of first function, that is 1. Okay, d by dx of x is 1. So this is the result that we get after applying this operator for the first time. Now we have to apply this operator for the second time. So this will be, again within this bracket you have two operators. So first we have to apply operator x on this function, that is a multiplication operator, and then we have to apply the second operator d by dx. So this is d by dx of, this is a multiplication operator, let us operate x square, x into x square into df by dx plus x into f of x. Okay, now in the final stage we have to apply this on, the term inside the bracket. So we get the final expression. Here you have two functions, so we have to apply the product rule. First function into differentiation of second function, so it becomes d square f of x by dx square plus second function d f of x by dx into differentiation of first function, that is into 2x, plus this operator is applied on the second term, which is also multiplication of two terms. So again we have to apply the multiplication rule of differentiation. So plus first function into differentiation of second function plus second function into differentiation of first function, that is 1. So let me write the LHS, that is d by dx into x square of f of x. Let us simplify this term. Here I have df by dx into 2x. Here I have df by dx into x. So if I add them, it becomes, so the first term is as such, d square f of x by dx square plus this term, if I add, it becomes 3x into d of f of x by dx plus the last term is f of x. So if I remove f of x as a common term in all the three, it becomes x square into d square by dx square plus 3x into d by dx plus 1 into f of x. This is equal to d by dx into x square of f of x. As I already told you, to obtain the final operator equation, we have to remove or lift this arbitrary function. Okay, because f of x is now factorized or factorized out in both LHS and RHS, you can remove this function and you get the corresponding operator equation. D by dx into x square is nothing but x square d square by dx square plus 3x into d by dx plus 1. So this is the expression for the operator d by dx into x square. So problem 10 is similar to problem 9. You are given a operator d by dx plus x square. So you have to find out an expression for d by dx plus x square. I leave it as an assignment to you while I conduct the online class. I will ask for the expression. So you have to use the procedure that I used for the earlier problem. Okay, so you take some random function f of x and try to apply this operator on the f of x and you get a final term. What you have to do from the final term is remove that arbitrary function and you will get the corresponding operator equation. Now let us concentrate on the 11th problem about the Hermitian operator. Okay, so you are given two functions, f of x and g of x. Okay, f of x is a complex function e to the power ix and g of x is a real function sin x, and the operator a is d square by dx square. You have to prove that it is a Hermitian operator, and also since both, if a is an Hermitian operator and these two are the eigenfunctions of a, find the eigenvalues. Okay, this second part of the problem I will leave it to you as an assignment. you have to tell me what are the eigenvalues of f of x and g of x uh, of the Hermitian operator. Okay, so first let us prove that this is an Hermitian operator. Since one of the function is a complex function, we have to use the second condition for Hermitian operator, that is integration minus infinity to plus infinity f of x star into a of g of x into dx is equal to integration minus infinity to plus infinity a of f of x star into g of x into dx. So if this condition is satisfied, then the operator is a Hermitian operator. So let us begin with take LHS first. Integration minus infinity to infinity f star of x into a cap of g of x into dx, which is equal to integration minus infinity to plus infinity f star complex conjugate of e to the power ix. What is the complex conjugate? You have to change the sign of the imaginary number. So here you have e to the power ix, so the complex conjugate will be e to the power minus ix into operator a d square by dx square of g of x, that is sin x, which is integration minus infinity to plus infinity e to the power minus ix, double differentiation with respect to sin x. First differentiation gives cos x, the second differentiation of cos x gives minus sin x, so minus I will take from the integration, so minus sin x into dx. So we need not evaluate this integration because we are not interested in finding out the final expression of this integration, so we will keep it as such. Now let us take the RHS. What is RHS? Integration minus infinity to plus infinity a cap of f of x star into g of x into dx, that is integration minus infinity to plus infinity operator a d square by dx square of e to the power ix, its complex conjugate into g of x, that is sin x into dx. Okay, I will separately find out what is d square by dx square of e to the power ix here. So this is nothing but d by dx of e to the power ix, that is d by dx of differentiation of e to the power ix is e to the power ix into I. And if again I differentiate this, I is a constant, so I into differentiation of e to the power ix, which is I into differentiation will again give I into e to the power ix. I into I is I square, which is minus 1 into e to the power ix, which is minus e to the power ix. Okay, so the value of this term is minus e to the power ix. So this is minus, I will remove from the integration, minus integration minus infinity to plus infinity. This is minus I have already taken out, so e to the power ix star into sin x into dx, that is equal to minus integration minus infinity to plus infinity complex conjugate of e to the power ix is e to the power minus ix into sin x into dx. So the LHS term and the RHS term are equal to each other. So we have proved the condition, therefore A is a Hermitian operator. Therefore LHS is equal to RHS, which means that A is a Hermitian operator. And remember, I told the two important property of Hermitian operator. Out of them, the important one is the eigenvalue of an Hermitian operator is always real, whether the function is complex or a real function. So when you are calculating the eigenvalues of f of x and g of x, concentrate on the eigenvalue of f of x. Though f of x is a complex function, if you find out its eigenvalue is a real number, though the function is a complex function. So by this you can by using this method you can prove that any given operator is a Hermitian operator or not.